Welcome back to the Iclix Academy. In our previous lesson, we configured an EBGP session between our ISP and two directly connected customers. In today's lesson, we'll look at a common real-world scenario where the customer is no longer directly connected to the ISP. Instead, the customer has moved their infrastructure into a data center. Imagine your customer has rented rack space inside a data center. The customer installs their Mikrotik router inside the data center and requests a BGP peering session with your ISP. Your ISP router is located in your core network, while the customer router is located inside the data center. Between both routers is the data center's transport network. Although IP connectivity is still working, the BGP neighbors are no longer directly connected. By default, EBGP uses a time to live (TTL) value of 1. Every time a packet passes through a router, the TTL is reduced by 1. Since our BGP packets now have to pass through the data center router, the default TTL expires before reaching the customer. To solve this, we enable EBGP multihop and increase the TTL to 2. This allows the BGP packets to travel across multiple router hops and successfully establish the neighbor relationship. Md5 authentication. Md5 authentication protects the BGP neighbor relationship by requiring both routers to use the same shared password. If the passwords match, the BGP session is established successfully. If the passwords are different, the BGP session will fail, even if IP connectivity and EBGP multihop are configured correctly. This provides an additional layer of security by preventing unauthorized devices from establishing a BGP session with our router. Now that we understand what EBGP multihop and Md5 authentication are, let's move into Mikrotik Router OS v7 and configure both features step by step. Although the physical links are connected, the ISP cannot yet reach the customer's point-to-point IP address because it doesn't have a route to that network. Before we can establish a BGP session, both routers must first be able to reach each other at the IP layer. We're using static routes to provide that connectivity through the data center transport network. Once the routes are installed, both routers will be able to communicate using their point-to-point IP addresses. Now the ping is successful. This confirms that the ISP can reach the customer's point-to-point IP address through the data center network. With IP connectivity working, we're now ready to configure our EBGP multihop session. The ISP belongs to Autonomous System 65001. For this lab, I'm using the ISP's point-to-point address as the router ID. A router ID uniquely identifies the router in BGP. I'm also enabling multihop because customer A is not directly connected to the ISP. The BGP packets must pass through the data center router. Customer A belongs to AS65010. Since the ISP and customer A use different autonomous system numbers, this is an EBGP relationship. Multihop must also be enabled on customer A because the BGP neighbor is located beyond the data center transport router. Remote address. This is customer A's point-to-point IP address and the address with which we want to establish the BGP session. Remote AS. This must match customer A's autonomous system number, which is AS65010. Local address. This tells the ISP which source address it must use for the BGP connection. In our lab, we're using the ISP's point-to-point address. Local role. The role is EBGP because the ISP and customer A belong to different autonomous systems. Connect. Connect allows the ISP router to actively initiate the TCP connection to customer A. Listen. Listen allows the ISP router to accept an incoming BGP connection from customer A. Multihop. Multihop allows the BGP session to establish even though the ISP and customer A are not directly connected. The session is now established. Even though the ISP and customer A are separated by the data center router, EBGP multihop allows the BGP packets to reach the remote neighbor. In this router OSV7 lab, enabling multihop is sufficient, so I'm leaving the manual TXTTL field blank. The customer will advertise a separate public IP prefix, such as 203.0.113.0/24, to the ISP. This matches how BGP is commonly deployed in ISP environments. Md5 authentication protects the BGP connection by requiring both routers to use the same shared key. If the keys do not match, the BGP session will fail even though IP connectivity and multihop are working. For a production network, use a strong and randomly generated key rather than this simple lab example. In this lesson, we established an EBGP multihop session between the Iclix ISP and customer A through a data center transport network. We used the point-to-point addresses as our BGP neighbor addresses, enabled multihop because the neighbors were not directly connected, and secured the session using Md5 authentication. We also demonstrated that the BGP session fails when the Md5 keys do not match. Before attempting this lesson, make sure you've watched BGP Part 2, where the basic router OSV7 BGP template and connection settings are explained in more detail.